Differential equations, I think, is a really mathematically interesting subject, but it's also a really, really useful subject. And one of the things I want you to know from the start is how useful it is. And just for you to have a flavor of a few of the ways in which differential equations get used to describe stuff in real life. Now, in the span of this little pencast, there's not too much I can do. I'll show you a few concrete examples, and before I do that, I just want to mention a bunch of big fields, right? So differential equations gets used in immunology to describe, the way that immune cells and T cells and other kinds of cells fight disease in your body. Differential equations get used in epidemiology, which is the study of, how disease spreads through a population. Climate science, that's a huge one these days. Our Earth's climate can be modeled with differential equations. Engineering, tons of differential equations in all different fields of engineering. Image processing and animation, so the way that animation is done and the way that processes are performed on images in Photoshop and things like that. Some of those are built around ideas from differential equations. Economics and mathematical finance, certainly many things in the economic world can be modeled with differential equations. And I think in the vein of keeping things simple, I'll show you just a couple of concrete, very basic examples. So let's start with population growth. So pretend we have a population of some organism, maybe it's, bacteria in a petri dish or something, and P of t is the function that describes how many members of that population there are at time t. Well, the most basic differential equation population model is dp dt equals rp. So to interpret this, remember that a derivative, one interpretation of a derivative is as a rate of change. So this equation says the rate of change of population as a function of time is some constant times that population. And here I've written that constant r is positive. And so this is describing growth. It's describing a situation where dp dt is positive, so the population is going to increase. And you can think of that value r as being almost like a percentage growth rate or something. Like the population grows at 3% a year, means that every year you get 0.03 times the population extra on top of what the population was previously, right? So this is the most basic differential equations population model. And you'll probably learn how to solve this one a little bit later on. Here's another really interesting and really important model for population dynamics. It's called the logistic model. So it looks like the previous model, except there's an additional factor of 1 minus p over k. And so again, r is measuring something about the growth of the population, and k is what's referred to as a carrying capacity. And this has something to do with, what's the maximum amount of population that can be supported by the environment. So if you're bacteria growing in a petri dish, the population can't grow forever because there's limited food and limited space in that petri dish. And so this is sort of the simplest differential equation that accounts for those kinds of constraints. Here's another example. This is like the simplest example in the financial world. So you have a savings account. B of t is the balance in dollars at time t, and your balance earns interest that's compounded continuously at some rate r. Well, the differential equation that describes this is dB dt equals RB. It looks actually just like the first equation we studied above. So it's like your population of dollars is reproducing in your bank account. And you can use this to answer questions, right? Things like if I know what the continuous compounding rate of interest is in my account, and if I hope to have, $1,000 by the end of 2 years, how much do I need to put into that savings account right now? Questions like that. Okay, here's another one of my favorites. This is epidemiology. This is just an example of like the simplest model for the spread of disease, or one of the simplest models for the spread of disease through a population. So here, S is the number of people in the population susceptible to the disease, I is the number of people who are infected by the disease, and R is the number of people removed from the population, either by having had the disease and recovering and becoming immune, or perhaps removed from the population, possibly by death, one or the other. Okay, so I've written down the equations here, and they basically just describe the fact that infecteds and susceptibles encounter each other, and when they do, there's some probability that that encounter leads to the susceptible person getting sick. The infected people similarly stay infected for some amount of time, and they have a recovery rate at which they enter in, or a death rate at which they enter into the R class. And so in this model, beta has something to do with the transmissibility of the disease, and nu, the Greek letter nu, has something to do with like how long you stay infected for before proceeding to the R class. And you shouldn't understand these equations in any depth right now. I'm just trying to give you a flavor for the kind of model that you will see in differential equations. And one of the really cool things about this model is even just this simple SIR model of 3 differential equations agrees amazingly well with some real public health data. And the most famous example is some data from the very early 20th century about the outbreak of the plague in Bombay. So very cool stuff.